You might be asking the question, well, how do we know about these steps? Or how do we know that there were two steps? This one took place first, this one is next, if you didn't see it. And that's a legitimate question. Well, we can do that via few ways. One of them is thermodynamics, the other one is kinetics, and of course, spectroscopy. So the idea here is we need the help of thermodynamics, kinetics, and spectroscopy to let us know what happened in between. Let's begin now with thermodynamics. Now, again, before we start, this is a brief, really brief overview of thermodynamics, something that you should have examined in Gen Chem 2. But we will only take the relevant portions. I will go over it quickly. Nevertheless, you are expected to know the non-mathematical. What I mean by this is there's no calculations in here, unlike what you did in General Chemistry 2. Here, we just need to understand what those mathematical expressions tell us, and of course, their values. So let's begin. Thermodynamics describes the energy, thermo, of course, from heat, and heat is a form of energy, describes the energy and equilibrium. We already talked about equilibrium. You ask two legitimate questions when you have thermodynamics, when you study thermodynamics. Very important questions is how do the energies of reactants and products compare? Is one higher than the other? Which one is? They will never be the same. What are the relative amounts of reactants and products are at equilibrium? Remember when we did that in acids and bases, we talked about where does the equilibrium shift? Well, it shifts toward the portion that has more products. And that shift, of course, is governed by the energies of those products. So your reaction is very unlikely to go if you form unstable products. So keep those questions in mind, is energy and equilibrium. So first, to study energy, we have to actually look at equilibrium. So the equilibrium constants, if you remember from General Chemistry 2, we did talk about it briefly in acids and bases. KEQ is a mathematical expression that relates the amount of starting material and products at equilibrium. So here's equilibrium. You have A and B as your reagents, starting material and reagent, and then these are your products. If you recall the KEQ expression, you took the concentrations of the products. So these brackets means concentration. So C to the exponent S, the coefficient becomes the exponent, D to T over A to M times, of course, B to N. Very well. So the size of the KEQ tells us the position of the equilibrium. That is, it expresses whether the starting materials or the products predominate once the equilibrium is established. So here's the important statements. And you can use numbers to verify that, by the way. Number one is that when the equilibrium is greater than 1, the equilibrium, in this case, favors C and D, the products C and D. And the equilibrium lies to the right as the equation is written. So when it's bigger than 1, it favors, again, C and D. When it's less than 1, it favors the starting material. The equilibrium lies to the left, of course, as the equation is written. So think about it. You can plug in any numbers to verify this. If your numbers on the top are larger than the numbers on the bottom, right, This indicates again, or if you have a KQ that gives you a large number, it means again your numerator is bigger. So in this case, we're going to say the numerator is bigger. Here, your numerator would be smaller, bigger than denominator. We're just going to call it DEN, denominator, just to shorten that. Here, whatever. Numerator is smaller. That's why you get KQ of larger than 1 or smaller than 1. So this is key. Very important to remember what is said here. Very, very important. Now, how do we relate this to stability? So it goes like this. The more stable the compound, the greater its concentration at equilibrium. So again, this is what you should be thinking about, is if it is more stable, then we are more likely to form that compound. So if the products are more stable than reactants, this can only indicate that the concentration of the products is greater than the concentration of the reactants. And of course, that means KQ is greater than 1. If the products are less stable, it means we're going to form less. So they will be less than the reactants. And of course, in this case, KQ will be less than 1, less than 1, less than 1. To give you an example, we're not going to go into the calculations, but this is interesting to, or important to talk about. It is actually the change in free energy gives free energy, delta G naught, between the reactants and products, which determines whether the starting material or products are favored. So when we talk about stability, we're talking about energy. You would know this by calculating delta G. So delta G in this case would be the G of the products, free energy of the products, minus the energy of the reactants. Well, we have this equation right here. So if you recall from Gen Chem 2, again, we're not going to do any calculations, but we need to understand what the equation tells us. Delta G is related to the equilibrium constants via this equation right here. So, you know, this is the gas constant R. And of course, T is the temperature. In Kelvin. Very well. So then the following would happen if KQ is actually bigger than 1. If KQ is 1, then delta G becomes negative. Now, if you don't agree with me, all you have to do is plug in KQ, let's say of 2 or 3 or 4 or 5, etc. And that would give you a delta G of a negative. And this means the following: that the reaction will release more energy than it will consume. And therefore, the products are more stable because they have less energy than reactants. So think about this equation. Go back to this equation. If the products have less energy than the reactants, you will get a negative. Just keep that in mind. So if I have, let's say in this case, I have just giving you basic numbers. If I have a 5 and I have a 10, that's going to give me a negative 5. That's why I get a negative, which means, again, that the energy of the products is lower than the energy of the reactants. We don't get this, by the way. We get this. We get the delta, the difference. So that delta G, when it's a negative, it means, again, the energy of the products is lower than the energy of the reactants. Therefore, they're more stable. Now, the reverse is true. If you have KQ smaller than 1, let's say it's a negative value, you get delta G to be positive. And in this case, you have the reaction will consume now more energy. Then it will release. And what does that mean? It means that the products are less stable than, because they're higher in energy, than the reactants. Try not to, I know you're tempted to probably memorize this. Maybe, but understand what that negative means. Use these numbers. These helpful numbers are going to help you. So now if we switch them, watch what happens. So now if we take the 5 and the 10 or reverse them, the energy of the products is a 10. And this is a 5. This is going to give you now a plus 5. It's always a products minus reactants. So look here. Products have a higher energy than the reactants. Therefore, it's positive, which means the reaction will consume more energy than it will release. This is a nice way of actually summarizing things from your book. Take a look at it. Just remember what goes with what. If KQ is bigger than 1, then delta G is minus. KQ is less than 1, then delta G is plus. It's the reverse. This table right here summarizes the values that you need to look at how the delta G is related to KQ. So if you look here at this table, and let me just bring it up a little bit. Again, go back and see what we did, what we talked about. And of course, this table kind of gives you representative values for delta G and KQ at 25 degrees. You might say, okay, well, what's the difference between, one number or one whole number? The difference is huge. If you have negative 4.2, okay, and again, delta G is negative, means KQ is very large, right here, bigger than 1. So it means the energy of the reactants of the products is lower than the energy of the products. Sorry, energy of the products is lower than the energy of the reactants. Look at this. You have 1,000 times as much B as A. This is your product, B, and A would be your reactant. So if you have now negative 2.8, so now you're going back up, that value is increasing, your KAQ is changing. It is now 10 times less. So there's 1,000 here, now it's 100. This is now 100 times as much B as A. If you decrease it, it goes down 10 times. Now it's 10 times as much B and A, all the way to, again, where you see delta G is 1,000 times now. In this case, when it's a plus 4.2, the complete opposite of this, KQ is very small, less than 1, 10 to the negative third is 0.0011 1,000th. That would be 1,000 times as much A reactant as B. This requires time, so take a minute, absorb what this information is trying to tell you, and then, of course, we can go over that when we meet.